Hey there, remember that feeling? Getting a brand new phone, that rush of speed, that crystal clear screen? It's like we're hardwired for progress, always looking for the next big thing in electronics.
And this time, it might not be just an upgrade, it might be a total revolution.
We're talking about 2D materials. I mean, imagine materials so thin they practically exist in two dimensions.
Yeah, we're talking about things like transition metal dichalcogenides, TMDs for short.
Catchy.
They're essentially a sheet of atoms as thin as you can physically get, but they have these off-the-charts properties like super strength, conductivity.
The CarSci article we're diving into today even mentions they adapt to their environment, which is kind of wild, but they're almost like too sensitive for their own good.
It's true. That sensitivity, it's a double-edged sword. On one hand, it makes them incredible for sensors, but on the other hand, manufacturing, even a speck of dust can mess everything up.
So it's like finding out the world's fastest race car needs to be kept in a hermetically sealed bubble.
Exactly. And traditional cleaning methods, forget about it.
Right, because soap and water aren't exactly high-tech solutions here.
It would be like taking a sledgehammer to a microchip.
Okay, so the article does get into why that is. Can you unpack that a bit for us?
Sure. See, a lot of those traditional cleaning methods, they use chemicals, right? And those chemicals, they can actually etch the surface of TMDs, or even worse, leave behind this residue that interferes with conductivity.
So like a circuit board, but the connections are all gummed up.
Precisely. The article specifically mentions hydrofluoric acid. It's often used in cleaning semiconductors, but for these materials, it's way too aggressive.
So we're talking about something that's both incredibly promising and incredibly fragile.
Yeah.
It's like, I don't know, trying to balance a house of cards on a windy day.
Yeah.
How do you even begin to clean something like that?
Well, that's where this CarCI article, it takes a turn for the, dare I say, cool. They dive into this new cleaning method.
Okay.
It's called reactive plasma cleaning.
Reactive plasma cleaning.
Yeah,
Sounds kind of intimidating, like something out of a sci-fi movie.
it does. It really does. But it's very real and very effective.
So, okay, walk me through this. What are we talking about here?
So essentially, it involves creating a plasma, which, that's a superheated, electrically charged gas. I like to think of it kind of like lightning in a bottle, but, highly controlled.
Right.
And this plasma, what it does is it interacts with the contaminants on the TMD surface.
Yeah.
It breaks them down into these harmless byproducts that can be easily removed.
So instead of scrubbing with chemicals, we're basically talking about vaporizing the contaminants.
Yeah, it's incredibly precise.
And this is all actually doable.
Oh,
Yeah.
okay.
And the article really highlights three major advantages to this method.
Okay.
So first off, it's incredibly effective,
Okay.
even against those really stubborn contaminants,
Well-
the ones that just love to cling to the TMD surface.
Around microscopic barnacles.
Exactly.
Okay.
The second thing is that it's incredibly gentle. Remember we talked about like traditional methods, how they could potentially damage the materials.
Yeah. This plasma cleaning, it operates at a much lower energy level.
So it's not going to mess up that very delicate structure.
Exactly. It can break down those contaminants without harming the actual TMD.
Okay, so it's effective, it's gentle. What's the third big advantage?
This is what I think is really exciting. It doesn't just clean the TMDs.
Yeah.
It actually restores them back to their original state.
Oh, wow.
Yeah, so remember all those incredible
The
properties?
strength, the conductivity.
All of that. This cleaning method brings it all back.
Really?
It's like hitting the reset button on the
Yeah.
material itself.
So we've got these crazy thin materials and this cleaning method that's like space-age technology.
Mm.
Where does it all actually lead? Like, what's the real-world impact here?
That's the cool part. The article, it lays out some potential applications, and they're big. Transistors, flexible electronics, even super sensitive sensors.
All right, let's take those one by one. Let's start with transistors. Those are, what, the tiny things that make our electronics work.
Yeah, they're like the little gatekeepers of electronics, controlling the flow of electricity.
Right.
And with TMDs, we're talking about transistors that are tinier, faster, way more efficient. Imagine your phone, but it doesn't just last longer. It can handle stuff that would make today's supercomputers break a sweat.
Oh, okay. So we're talking like next-level computing power here.
Oh, yeah. Artificial intelligence, faster drug discovery, even better climate modeling. It's a huge leap.
Okay, that's wild. What about these flexible electronics? The article mentioned those two.
Right, so imagine electronics that can bend, fold, even stretch without breaking.
So no more cracked screens.
Think bigger. Phones that wrap around your wrist, screens that practically unfold from your pocket. We could even have clothes that are basically interactive displays.
That's straight out of a sci-fi movie.
I know, right? But that's where we're headed. This isn't just about convenience, it's about totally changing how we interact with tech, with the world around
Like
us.
a whole different future for, well, everything.
Exactly.
Okay, one more from the article, those super sensitive sensors. What's up with those?
So, because TMDs are so crazy sensitive to their surroundings, they can pick up on these tiny changes that regular sensors wouldn't even notice.
So we're talking like really, really tiny.
Think like on a molecular level. Imagine medical devices that could diagnose diseases in the earliest stages. Environmental sensors that can spot pollution with insane accuracy. Heck, even wearable tech that could track your health in ways we haven't even imagined.
Okay, so this is all super exciting.
Yeah.
But science is a process, right? There have to be some challenges too. What did the article say about that?
Right, it's not all smooth sailing. They did mention that while this reactive plasma cleaning works really well, we still need to do more research. Like, how long does the cleaning last? Does it impact the TMDs over a longer period? And can we even scale this up from the lab to, actual mass production? Those are all things to figure out.
So, huge potential, but still early stages. And that's a good place to wrap up our deep dive today. Seems like we're on the edge of this materials revolution, and TMDs could change everything. But it's a good reminder that the big breakthroughs always come with big challenges. And sometimes figuring those out is just as important as the discovery itself. Thanks for joining us.